Welcome, everyone, to today's DSIAC webinar on additive manufacturing of 3D printed energetic structures. Before I hand it over to Monique, I would like to do a quick introduction on DSIAC, and then we will hand it over to her for the rest of the time frame, and then have a little bit of time at the end for questions and answers. If you have questions, there should be a little dialog box in the top center of your screen. Otherwise, Caitlin and I will try to put your questions in the chat box into the dialog box for questions at the end. Once again, my name is Travis. I'm from DSIAC. We would like to welcome you to our May presentation, and just to give you a little heads up, we are the Defense Systems Information Analysis Center, or DSIAC, one of the 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our webinar series highlights current and emerging research and technology developments in the DoD and presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports these working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. If you have questions, inquiries, you can reach us on our website, submit a technical inquiry, which is 4 hours of free research. And if you have any technical difficulties during this, we will be recording this and send out the link afterwards. And if you can also call in, and I will post the slides for this if you call in the chat box. For the remainder of the time, I'd like to hand it over to Monique.
Thank you very much. I'm excited to talk to everyone today about additive manufacturing of 3D printed energetic structures and about some future work that we'll be doing building off of this. So I thought that I would introduce myself first. I'm an incoming assistant professor at Purdue University, and I start in August, so in a few months. And in the meantime, I've been a research scientist for almost a year now at Oak Ridge National Laboratories. And my role there has largely been on developing anomaly detection algorithms to detect defects that might occur while you're 3D printing different composite materials. And before that, I received my PhD at Purdue University almost a year ago at this point. And largely, I was working on 3D printing energetic materials. And that will be, my PhD work will mostly be the highlight of this talk today. I also thought it'd be interesting to share an additional aspect of myself. So on the right here, I have a picture of me holding my very first solid rocket motor as a freshman at UCSD. And my sister actually bought me this shirt, but it says, "The only reason I became an aerospace engineer was so that I could build my own Starship Enterprise." So I know I'm not necessarily building a warp drive here, but that is largely what drove me to working in propulsion and on energetic materials. So that still inspires me to this day. Moving on, essentially my team's research focus is largely on developing the manufacturing science that is going to be necessary to create additively manufactured energetic materials, or AMEMs. So additive manufacturing is very interdisciplinary, and so are energetic materials. So this is going to involve everything from developing the material science necessary for 3D printing, to developing custom 3D printers, to detecting defects and introducing quality control, to designing combustion experiments and analyzing these additively manufactured structures. So essentially our goal is to be able to create complex geometries and multiformulation energetics to kind of push the boundaries of what they can currently do. So today I will first give an overview of why would we want to 3D print energetic materials, and in particular I'll be focusing on solid composite propellant because that is my main background, but this is applicable to other energetic materials as well. Then I'm going to talk about a few case studies on 3D printing composite propellant. So first I'll talk about how we use a technique called vibration-assisted printing and how that allows us to print propellant without losing any combustion performance. Then I'll be talking about adapting photopolymers to propellants so that we can create complex structures. And then lastly, I'll be talking about creating layered propellants, so multi-formulation propellants, and I'll focus on a modeling study and an experimental study. And then if I have time, I'll briefly highlight on some additional research interests for my team at Purdue University, and then I will wrap up this talk. So first of all, what are energetic materials? In our life, essentially they are chemical compounds that when you break the bonds, you can release a lot of energy from them. So they could be anything from explosives, pyrotechnics, propellants to fuels. So explosives can be useful for demolition or national defense. Propellants can be useful for space exploration. Pyrotechnics provide us a wonderful 4th of July fireworks show every year, and fuels can largely be used for transportation. And of course, the application of energetic materials are in anywhere from government to industry to everyday consumers like ourselves. However, energetic materials can be very dangerous if not handled properly. They typically have pressure and temperature dependence. They can be sensitive to humidity, among other factors. So it's very important to be able to have control over how you design these energetic materials so that you maximize their function while maintaining safety. So in particular, I will be talking about a subset of energetic materials. In particular, I will be talking about composite solid propellants because that is the main basis of this talk here today. So composite propellant is essentially a mixture of a high solids loading of particles held together by a small amount of polymer binder. So the particles that you might find in a solid propellant will be an oxidizer particle. So ammonium perchlorate is a very commonly used oxidizer in composite solid propellant and typically makes up the majority of your solids loading. You can also include other particle additives such as aluminum, iron oxide, or others, and typically you add them to help improve the burning rate of these propellants by either raising the flame temperature or lowering the decomposition temperature of ammonium perchlorate. And typically, when you combine the oxidizer and the additives, that can make up about 85 or higher solids loading or weight percent in your mixture. So, the higher your solids loading is going to be of your particles, that's going to make your propellants more difficult to process because it's going to be more viscous. And the same thing applies if you use a lot of small particles. So, for example, if you use a lot of nano-aluminum, that's also going to increase the viscosity of your mixture. The binder is typically a small percentage of your propellant, and the way it works is that first it starts off in a liquid state, but then with some heat, you can thermally cross-link that polymer, and then it cures into a solid state. And that is essentially what holds the propellant together. So first, when you're mixing the propellant with mixing the particles together with the binder, it starts off in a slurry state. So I like to think of that as the consistency of wet sand, for example, and then you pour that slurry into a predetermined mold, and then after you thermally cross-link it, it cures into a solid state, and I like to think of that consistency like an eraser, essentially. So it's very important to consider your formulation when you're processing your propellant and manufacturing it, but it's also important from a combustion standpoint. If you don't have a high enough solids loading, your propellant's just not going to sustain combustion, or it's going to be unstable. So it's important to, have, in order to have a high performance propellant, you need to have a decent solids loading, but that could potentially provide manufacturing processing challenges. And then here, just on the right, just to demonstrate, I have two examples of propellants that are cured. So the top is an example of a propellant with nano-aluminum. which is why it's gray. And you can see there's some larger AP crystals in there embedded with some smaller AP crystals. And then the same thing on the bottom, except that we have iron oxide instead, and that's why it's red. But you can see that we have typically, bimodal mixtures of propellants, large AP particles embedded with smaller AP particles, and then, the small additives like iron oxide or nano. So now that we understand what propellant formulations look like at a small scale, it's important to think macroscopically about how our propellant design influences a solid rocket motor. So typically in a solid rocket motor, you have your propellant grain inside of that. And once you ignite that propellant grain, it's going to pressurize over time in a specific way, and that is how you generate your thrust. So if you look at the equation below with T equals CF PC AT, essentially you can see that thrust is directly correlated with your chamber pressure, which is going to be determined by how your propellant grain self-pressurizes. When you look at the figure in the bottom left, you can see that, you can have quite a bit of control over your pressure or thrust curve. So you could potentially be accelerating over time, decelerating, or maintaining speed. And it's important to have control over this thrust curve because that could be very mission dependent. So in addition to that, your solid rocket motor, the way it pressurizes is going to be dependent on essentially how it is consumed in the motor. So if you look at the equation on the top right with m dot equals rho RAB, essentially the main factors in that equation are R, which is the burning rate of your propellant. So your burning rate of your propellant is dependent on the formulation of your propellant and the chamber pressure. So it's a little bit of a feedback because as your chamber is pressurizing, the pressure changes and that feeds back to your burning rate. But essentially, your burning rate is going to be related to pressure on a log scale. So you can fit two parameters to that typically. So A is just a coefficient, and then N is going to be your burning rate exponent. And those will tell you how your burning rate behaves as a function of pressure, essentially. Then another term that is important when designing your solid rocket motor grain is your burning surface area, which is AB, which is highlighted in red. And that is determined by the shape of your solid rocket motor grain. So this is essentially something we want to have good control over because that's going to be very important in our pressurization and therefore thrust curve. So this is exactly how, these are parameters we want to keep in mind when we're designing a solid rocket motor. So what is the...
Monique,
Yes?
wait, can you every once in a while just let those who are following along on phone know what slide you're on?
Oh, yes. Okay.
Thank you.
I will try to do that. So I'm currently on slide 7. So what does a solid rocket motor look like, or a solid grain look like in particular? Well, it can look like many different things, and it's going to depend on how you manufacture that. So essentially, the simplest type of solid rocket motor is going to be an end burner, where you completely fill up your inner chamber with propellants. But of course, that's just going to give you a constant burning surface area because you're really just burning a circular area the whole way down. More commonly, people will add a central port to their motor. So that's going to change your burning surface area over time as the surface regresses. The way that you make these central ports typically is by using a solid mandrel to kind of hold that space. So you will insert the mandrel into your motor grain, and then you'll pour your propellants around that. And then after your propellant slurry crosslinks, then you remove the mandrel, and that's how you get your core shape. You can potentially make more complicated structures in your propellant grain. So for example, you might be able to add fins or slots or grooves, but that could be more challenging to do with a traditional mandrel. So you could potentially use a chemically removable mandrel to do that, but you might still have residue left behind in your motor. Sometimes you can machine your grain, but that could be very challenging and potentially dangerous to do. And it's very important that you have control over how you process your grain, because if you accidentally create a defect in your motor, then it's going to burn erratically, unpredictably, and could potentially lead to catastrophic effects on your motor. So in theory, we want to be able to realize many different geometries so that we have more control over our thrust curves, but in practice, that can be difficult to do with current manufacturing methods. Moving on to slide 8. So another process that we might want to look at to help us realize these complex geometries is using a process called additive manufacturing, which is very commonly used in many industries nowadays. But essentially, it's a process of constructing a structure layer by layer rather than starting from stock material and removing material, which is called subtractive manufacturing. So how do we want to apply this to energetic materials? Well, essentially, with energetic materials, like I was saying before, one of our biggest goals is to have more flexibility over the geometries that we can create, because that's going to be very critical to how our motor burns, or in general with energetic materials, it's going to be very critical to the different combustion metrics and characteristics. And another thing we're interested in potentially is creating material gradients or layer anisotropy. So that could involve multi-material or multi-formulation additive manufacturing. So that, one example could be we have a propellant where like one region burns faster than the other, or perhaps you can have, some structural functionality in there or different mechanical properties. So we're really interested in leveraging these potential benefits and applying them to energetic materials. So the big Q or question for this presentation is, how can we use 3D printing to change how we make solid propellant? All right, slide 9 is just talking about our first study, which is printing live solid propellant. So we're on to slide 10 now. So how do we 3D print solid propellant? Well, at Purdue, we developed a custom technique called vibration-assisted printing. And what's unique about this technique compared to other methods out there, and there are many methods out there, is that we have the ability to print viscous mixtures, in particular, viscous heterogeneous mixtures, which is exactly what propellants are. And we can do it at a relatively fast rate and with a relatively high resolution. So the way that vibration-assisted printing works, essentially, is we have our custom material mixture put into a syringe, and then instead of just pressing it out with compressed air or a screw, we actually apply vibrations at the tip. And what's unique about that is that if we didn't have vibrations at the tip, essentially the material would just be sliding along these walls in the converging nozzle, and there'd be a lot of friction there. But when you apply these vibrations, the walls move relatively fast so that your material's not really experiencing the friction there, and it could just slide out rather quickly. So this allows us to print many different types of materials. In the bottom left, we've printed clays, different heterogeneous mixtures, and even food mixtures before. So this is the technique that we're going to apply to printing propellants. We're on slide 11 now. So the first case study here is that, okay, we have this technique called vibration-assisted printing, which could potentially allow us to print high-performance propellant mixtures because we can print viscous mixtures, and that tends to kind of correlate with a higher-performing propellant. But the main cue or question of this particular study is, how does VAP, or vibration-assisted printing, affect propellant combustion? And this is really important to answer because clearly, if we're going to take advantage of 3D printing, we don't want to lose any combustion performance by doing that, or at least not significantly. So the whole point of the study was to investigate that. In this particular study, we used 2 different propellant mixtures. So the only difference here is we used 2 different binders. The solids loading of ammonium perchlorate stayed the same, essentially. So the first binder we used was HTPB, which is a very common traditional solid rocket binder that thermally cross-links, and it takes a while to thermally cross-link, so it's a pretty slow process, and that can lead to propellant deformation. And then the other one that we used was a UV curable epoxy, and the idea behind this is to very quickly cure your propellant into its shape so it doesn't deform too much. Down here below, we have an example of a 3D printed propellant with the HTPB binder. So one thing you might notice is that we have very smooth surface finish. We're able to, print a relatively solid-looking strands. And we also compared these 3D printed strands to small-scale cast strands. But of course, looking at the surface isn't going to tell you the whole story. It's important to look at the microstructure. Slide 12. So again, we want to make sure there aren't voids induced by this VAP process, and the only way to do that really is to look at the microstructure to see if there's any correlation between voids, defects with our printing path or our printing process. So just to orient everyone, the top two images are cross-sections of propellants with HTBB as the binder. The bottom two images have the UV-curable epoxy as the binder. The left two images are cross-sections of 3D printed propellants, and the right two images are cross-sections with the UV-curable, I think I said that wrong, sorry. The left two images are cross-sections, yes, are 3D printed propellants, and the right two are cross-sections of cast propellants. So one thing that we noticed is that when we use HTBB as the binder and we 3D print it, there is some deformation in it compared to the UV-curable binder. And another thing that we notice is that the top two propellants, which both have HTBB as the binder, they both have porosity in them, which in them. About is, are these holes from our 3D printing process, or is this something else? So when we look closer at the densities of these values, or these propellants, and when we compare it to our UV-curable epoxy, our 3D printed UV-curable strand had essentially full density, and even the cast strand had relatively good density. So to us, that's saying that this could be a formulation problem, because if it was a 3D printing issue, we should see voids in our 3D printed epoxy strand, and we don't. So to us, that means that there must be something with our HBB formulation causing this off-gassing. And another thing we noticed is that our 3D printed HTBB strand had better density than the cast strand. So in some sense, vibration-assisted printing helped a little bit to reduce porosity, but our main issue here was formulation because we used an additive called tepanol, which is a bonding agent that is supposed to improve the bonding between AP particles and the binder, but it can produce a lot of ammonia during processing. So to typically mitigate that, you would have to mix it under vacuum for a long time, which was not done in this particular study. So the main takeaway here is that the voids were not due from our VAP process, which is promising. Slide 13. So the next thing that we did was we did some high pressure experiments where we compared the burning rates of cast HBB propellants and printed propellants. And essentially what we saw is that there's quite a lot of overlap in the points, so there really is no significant differences in the burning rate. The cast propellant might be slightly higher in burning rate, but that is only because it is slightly more porous based off the density. And we have our burning rate curve fits here. So if you recall, the formula for burning rate, or the curve fit for burning rate, is A times P to the N. So essentially, N is our pressure exponent, and this is in front our pressure coefficient. So essentially, the coefficient tells you kind of how offset these curves are, and the pressure exponent tells you the slope of these curves. So as we can see, there's not a lot of significant differences between the two. We also looked at the burning rate of the UV-curable propellants, and what we found is that although the slope was relatively the same, the burning rates were overall shifted downward, so they were less. So the trade-off is that although you can cure quickly with this UV-curable epoxy, it won't necessarily burn as well as HBB. But in general, the overall takeaway, or T, from the study is that we didn't see any significant changes in the burning rate from VAP, which is good. So we didn't really lose anything here. And we actually saw a slight improvement in the densities of our parts when we compare it to small-scale casting. Slide 14 is just introducing our next study, which is developing photopolymers for propellants. Slide 15. So now we've demonstrated that VAP does not negatively affect our combustion performance. But as we showed before, HBB takes a long time to cure, so our parts will deform, if we wait for them to thermally cross-link. So it's important to develop a photopolymer that, maybe has similar properties to HBB, that we can 3D print, that can cure relatively quickly, and that can handle opaque additives, because in solid propellants, it's very common to include opaque additives like iron oxide or aluminum. So if you have those additives, that could limit how much your photopolymer will cure. So our big cue for this particular study or question is, can photopolymers be compatible with propellant ingredients and cure formulations with opaque additives? So we designed a test to be able to do this because I couldn't really find much in literature on how to test how deeply, what is the cure depth of an actual propellant formulation. There are many studies on how photopolymers cure and what the functional groups are, but not necessarily how things cure when you have a lot of particles in them. So this study, we essentially used some commercial off-the-shelf photopolymer ingredients. Our photo initiator was BAPO, which cures at 365 nanometers. We used a polybutadiene urethane acrylate, which is very viscous and sticky, but if you mix it with some sort of diluent, you can kind of lower the viscosity to some sense and you can tailor it a little better. And the diluent we chose was HCDA because not only can it help tailor viscosity a bit, but BAPO is also slightly soluble in it. And we only use a very small percentage of BAPO. So we want to make sure that we can mix it thoroughly throughout our mixture. For the test that we designed, it was relatively simple, but essentially down in the bottom, you can see that we have a region of uncured propellants kind of pressed into a central circle on a petri dish. And then we will shine a UV light onto that uncured propellant for 45 seconds. And then once we turn the light off, we'll remove the cured propellant from the uncured propellants, and then we'll measure the thickness or the depth of that cure, essentially. And we, for the formulations, we essentially kept the solids loading the same, so it's 85%, and what we varied was the intensity that we cured at, the wavelength, and the aluminum content. Slide 16. So here on the right, this is kind of the main result of our study, although we did many other tests. But essentially, we showed that as we increase aluminum content, we're still able to cure relatively deeply with this photopolymer mixture. So we're able to cure, about 1 to 3 millimeters, which is good for us because when we 3D print a layer, we typically 3D print at about 0.25 millimeters or 0.3 millimeters. So if our cure depth was less than that, that would mean that our printed layer would have uncured regions in there, and that is just not desirable. For us, knowing that this will cure much deeper depending on the parameters we use, especially with highly aluminized propellant formulations, that means that we don't really have to worry about regions of uncured propellant. And this also means that maybe we can 3D print several layers before curing, so that might reduce a bit of our print time. So we also know that with this photopolymer mixture, we could potentially, swap out some of those components to tailor other properties more. So whether we want to tailor more cure properties or maybe mechanical properties, that can be done as well. Slide 17. Lastly, we looked at the microstructure of cured propellant. So we, in this image in the bottom left, we cured 4 different layers. And the point of this study was to see if there was any phase separation between the photopolymer and the particles, because in other studies I've seen that they use low viscosity photopolymers, which might separate from your energetic particles. So here we didn't really see that, so that was promising. And we also did a little bit of combustion on it, but essentially the main takeaway or T from the study is that we now have a potential photopolymer that is tailorable that we can use to 3D print more complex propellant structures. And we have a way to quantify the cure depth, which is an important parameter for this type of printing. Slide 18 is just introducing that we're moving on to layered propellant combustion and in particular modeling. So we know now that, we have vibration assisted printing and it can print fully dense propellants. We have a tailorable photopolymer that can allow us to cure more complex or create more complex structures. But another area of interest is multi-formulation printing. And we know that with vibration assisted printing that is possible, But it is important to think about modeling as well, because you may not always be able to 3D print certain structures or experimentally test certain configurations. So modeling can be a useful tool to help us gain insights on layered propellants. So the big cue for this particular study is, what is the combustion behavior of layered propellants, and what are the driving factors? So in order to answer those questions, we use a a legacy code called Rockfire, developed by Professor Tom Jackson and his co-authors or peers. And this code has been around for a long time. It essentially simulates propellant burning rates, and it's been validated for years. So it was definitely a good place for us to start. And down to the left image below, yes, the bottom left image is an example of what a simulated propellant looks like in Rockfire. So essentially you have all these different spheres, which represent different AP particles. So you can make it monomodal, bimodal, trimodal, so on, so forth. You can specify particle size distributions, specify solids loading, and everything that is not a particle in this cube is the binder, essentially. So it will simulate burning of all these different parts. For our particular study, though, we made a layered propellants. So we did 3 different types of layered propellants. So essentially, the way we did that was we kept the outer layers the same. So those were supposed to be slow-burning propellants. And then the inner layer, we changed the particle size. So we typically decrease the particle size in the inner layer so that it would potentially burn faster than the outer layers. So those are what the layer configurations look like. And we also tested 2 different orientations. So we tested what's called vertical orientation, where the flame surface is going to be above the layer propellants, and the middle layer is supposed to burn faster. So we should end up with some sort of curvature on the surface. And then the horizontal orientation is just rotated 90 degrees from that. And essentially, we will be seeing the flame surface go through the slow burning layer, then the faster layer, and then the slow burning layer. Slide 20. So here I have an example of some results from our Rockfire simulation with the vertical orientation. So just to orient you, the red and blue part is the solid phase or the propellant. So the red particles are AP and the blue is the binder. And as you can notice, on the outer edges, there are larger particles, and in the intersection, there are smaller particles. And that represents the 3 different propellant layers. And everything above that is the gas phase, or where the flame is. But one thing that was interesting about this was that we started with relatively flat ignition, which is typical in a single formulation propellant. But over time, we do get this increase in burning surface area. Slide 21. So we also looked at burning rate curves on this. So without getting into too much detail, the first part of the burning rate curve is just transient solution. And essentially what we did is we compared the burning rates of each individual propellant, which are the horizontal lines, the orange, purple, and dark blue, and then the yellow. And we compared that to the burning rates of the layered propellants, which are these 3 lines in the middle that have an increasing slope. So we do demonstrate that we can increase the burning rate by increasing the burning surface area in the vertical orientation. Slide 22. Now, when we flip our propellants 90 degrees and burn it in the horizontal orientation, we see something completely different with our burning rate curves. So again, just to illustrate, the first part is transient, and we still have those single propellant burning rates embedded in here for reference. So those are the brown, purple, dark blue, and yellow lines, which are horizontal looking. But we can see that as we burn through different layers and as we approach different interfaces, we get some dynamic results. So I know I don't have a cursor here per se, but the point where it says interface 2 on the plot is where we're transitioning from the slow burning layer with larger particles to a faster burning layer with smaller particles. And then interface 1 is when we're transitioning from the fast layer to the slow burning layer. So one thing you might notice is that at interface 1, we get this really large drop in burning rate, which is much less than the speed of the slow burning layer should be, which is denoted by the yellow line. And we also see some slight dips at interface 2. So in order to explain that better, we looked at a few other factors. So in the bottom plot, we superimposed the burning rate curve, which is denoted by the brown, with the surface area ratio, which is the blue line, and the equivalence ratio divided by 10, so it fits on this plot with the yellow line. The one thing that we notice is, when we're just about to approach interface 1, where we're at this higher burning rate speed, basically when it hits that interface, we get this really large increase in the equivalence ratio. And what that means is that we're actually going to be really, really field rich at this point, because we're going from fine particles to approaching coarse particles in the slower burning layer. So then that initiates this large drop in burning rate. But as we start kind of burning through this binder-rich region and approaching these coarse particles that we're igniting, first we start seeing the equivalence ratio head back down towards equilibrium, because we're starting to see some steadiness with the surface area ratio, because we're igniting, lots of different coarse particles, and it's not going to burn as homogeneously as if you have a bunch of fine particles. And then between this surface area ratio change and the equivalence ratio returning to equilibrium, we see recovery in the burning rate. So now we're actually back at the speed of the slow burning propellant layer. So I guess the main takeaway from this is, the orientation that you burn your layer propellants is going to be very, very important. Because in this case, we almost saw extinction when we burned these propellants horizontally. And particle size had a large effect in this, because like I was saying, when you're burning a bunch of fine particles, it's going to be burning a little more evenly compared to a bunch of coarse particles embedded in the binder. But the main takeaway of the study is that modeling can be useful to help us to kind of pre-screen different propellants that we want to put together, and help us kind of pre-screen factors we may not be able to test experimentally. Slide 23 is just talking about how we're exploring 3D printed layered propellant. So these are experiments now. So we've shown that modeling can be a useful tool, but now we also want to show in practice what layered propellants will perform like. So the question, or the cue of this study, is what is the combustion performance of 3D printed layered propellants? So in this study, we only tested 2 different types of layered propellant. The outer propellant layers were the same, so it's just ammonium perchlorate. And then the inner layer either had a little bit of nanoaluminum or a little bit of iron oxide, and we used an HTBB binder because we weren't printing these very tall. So essentially, each layer is approximately 1 millimeter. So the structure is only about 3 millimeters tall. Slide 25. These are microscopic images of the different layer propellants. So as you can see, the layers are relatively distinct from each other. There is maybe a little bit of deformation at the interfaces, but that could be because these are maybe not the most viscous mixtures. Actually, the nanoaluminum layer propellant has a better interface, I would say, than the iron oxide layer propellant. But essentially, you can distinguish the layers, and these are, again, at very small scale. We also looked at the density of these propellants. So we compared the densities of these layer propellants to the densities of cast single formulation propellants. And what we found was that, again, these printed layer propellants have better densities than their cast counterparts, and that is consistent with what we saw in the previous study, where vibration-assisted printing could give you slightly better density compared to small-scale cast propellants. Slide 26. So then we did some combustion experiments with these propellants, and the image on the left shows how they evolve over time. So the top sequence is of the layered iron oxide propellant, and the bottom sequence is of the layered nanoaluminum. So you can see that they start off igniting relatively flat, and then over time the surface area develops. But then at some point it seems to kind of stabilize and approach a steady state region where it doesn't really increase further. We did compare the burning rates of these layer propellants to the burning rates of cast propellants. And essentially what we found was that the burning rates of the layered iron oxide and the cast iron oxide, those curves were essentially the same. If you look at the table below or the middle image, you can see the top two curves, the black and the light gray curves, those are essentially overlapping, and the burning rate curves, the exponents are pretty much the same. It's 0.35 and 0.37. So that means that you only need a small layer of iron oxide to get that increase in propellant burning rate. The nanoaluminum was a little different. So if we look at the second image with the nanoaluminum on it, the burning rate of the layered nanoaluminum is actually a little bit less, or the curve is a little bit less than the cast nanoaluminum. And the reason for that is because we have a smaller, we have less nanoaluminum essentially in our layer propellants, and that will decrease the amount of radiation heat feedback to the surface that you would get if you had a strand completely made of nanoaluminum propellants. So that is our theory behind why there's a slight change. But at the same time, the pressure exponent of our nanoaluminum propellants is 0.44 compared to the cast nanoaluminum, which is 0.56. So typically in propellants, if your exponent's above 0.5, it may be a less stable propellant. So for us, it's actually good that our burning rate decreased a little bit. So we have a slightly more stable curve with a small addition of nanoaluminum. Slide 27. And just one more thing to highlight about the study is that since we're testing layer propellants, we had to identify some new metrics and create some new definitions here to describe the combustion. So one of those is what I call the transition time. Essentially, it is the time from when we ignite our propellant to when it approaches a steady state burning surface area. So essentially, what I mean by that is our surface length, called S, divided by the width of our strand, W, that is the ratio of interest to us. So if it's 1, that's pretty much flat surface ignition. But as it increases over time, there's a point where it doesn't seem to increase anymore. And once we reach that point, we call that the transition time. But essentially, in all of our cases, we found the transition time, as you can see, the plot is not that long. So it doesn't take long for us to see increases in burning surface area, which is good for us for practical application. So the main takeaway from the study is that we, created some key metrics that are useful for describing layered propellant combustion. And we also saw that you don't need a lot of catalyzed or enhanced propellant to increase the burning surface area. So that could be useful if you have an expensive additive. Maybe you don't need to make the whole propellant with that additive. You could just selectively 3D print regions with that faster burning propellant. And we also saw a little bit of a slight improvement in the burning rate exponent with our layered nanoaluminum. Slide 28. So I'm not sure if I have time, but I guess I'll just go through 2 slides and then I will conclude real fast. So now kind of building off of the work I've done before. So everything I showed you before is some initial work that has demonstrated kind of some of the benefits you might reap from 3D printing these propellants or energetics. But in addition to continuing those research areas, my group would also like to focus on 2 other things. So I'll try to keep it short. But one other area we'd like to focus on is what I call dissimilar material printing. I like to think of that as more extreme multi-material printing. So that involves 2 very different materials, 2 very different processes. So one example of that is if we use fused filament fabrication, where we can customize and make reactive filaments and we can 3D print that with fused filament fabrication. And then we can combine that with vibration-assisted printing, where we know we can print propellants. And the reason we want to do that is because in the past, we've shown if we embed these reactive filaments in propellants, we could very quickly open a port dynamically with that process. So that is the image on the right. So instead of just casting this empty central port in a traditional solid rocket motor, you could actually have something energetic there that contributes to the reaction but rapidly increases the burning surface area. The only thing that we haven't really done yet is 3D print both components together, and I think that's going to be necessary to create really complex geometries. So clearly this is going to involve customized 3D printers, some material science to enhance bonding, and some really interesting design process here. But this doesn't just have to be applicable to energetics. We could potentially use inert thermoplastics to provide some structure for propellants, like a thermoplastic lining, or we can make small integrated propulsion systems that are made out of thermoplastics, and then we embed energetics into them. So there are many different possibilities here. And then lastly, process monitoring is going to be really important for 3D printing energetics. Excuse me. So this is leveraging my experience at Oak Ridge National Labs, where I'm working on creating anomaly detection algorithms to detect anomalies in our 3D printing process. So here, if you have defects in your energetic materials, that could be very, very dangerous and catastrophic. So it's important to be able to catch those defects before you actually burn this defective energetic material. So that process is going to involve integrating sensors into the 3D printer, analyzing those sensor signals with techniques like machine learning or statistical process control or both. And then the idea is that, if you have one bad batch or one bad seed in your batch, you should be able to detect it as you are 3D printing. So I'm going to skip these two, and then I'm on slide 33. So just to wrap up, 3D printing energetic materials is a relatively new field, and there's a lot of work that we need to do to fully develop the manufacturing science necessary to use these in application. So one unique thing about my group is that we have experience along the whole production line of AMEMs. So, we're not just material scientists or combustion people or people who work in manufacturing. We understand each step. We understand the terminology in each step. And I think we can help bridge, we can link these together to make more cohesive design of AMEMs and to qualify them. So with that, collaborations are welcome. And I would like to thank everyone for helping me speak today. So thank you. I'm done.
Okay, thank you so much, Monique. And it looks like we got a few questions at least that I will put up, and I will read them out loud for those that are dialed in, and answer to the best of your ability. I will also mention that this has been recorded, and we will be uploading the recording afterwards. And if you have any further questions on this after the presentation, you can either reach out to DSIAC on our website, or reach out to Monique, or you can reach out to us and we will get you in contact with her. Now for some of the questions. Have you optimized the particle size of the solid materials to minimize viscosity?
No, so initially we were just testing, I guess in the first study we used a lot of fine particles because we were using HGBB and we didn't want the structure to deform too much. So we used a non-optimized ratio of large particles to fine particles. So we didn't really optimize it for combustion purposes or solids loading, but we were kind of just trying to make it stiffer for 3D printing. But yeah, that is important to consider. But there's a lot of data on different optimized particle loadings for traditional motors, or propellants, I guess.
Okay. Next question. You gave the weight percentages of solid fraction of the propellant, 85%. Do you know it in volumetric terms?
Yeah, so in some of the 3D printing studies I showed, we had, I think, 73 and 76 volume percent, and I think I've even done slightly higher than that, but in the 70s range typically.
Okay. Printing causes compression, question mark?
I think if this is what I understand correctly, I think you're saying that in the syringe, you're kind of having some, that's, yeah, kind of the compression in there is helping to improve the density. And I would say yes to some degree, because there's a little bit of back pressure in there. It's mostly to help feed the reservoir material down to the nozzle, not push it out of the nozzle. But yes, I would say that has some effect on the propellant density, and maybe the vibrations also have some effect.
Okay. What is the absorption coefficient depth of AP at 365 or 395 nanometers? Is it opaque at that wavelength?
I do not know the specific answer to that question, but from observation, it did not really seem to be opaque at that wavelength. AP is relatively clear, and if anything, I think the AP helped create some of those larger cure depths, because we did compare. We also looked at the curing of the photopolymer by itself, and it didn't cure as deeply as with the AP particles in it. So I think that helped kind of scatter the UV light deeper, and that kind of led us to larger cure depths.
Okay. Do you have any issues with line shrinkage due to rapid curing or residual stress in the final test article due to curing speeds with the photopolymer system?
So there is shrinkage. We haven't specifically qualified that, but it's very apparent from looking at the parameters. And I would say there's more shrinkage when you have higher intensities, but that has not been qualified. We want to continue looking at mechanical properties, because if you're carrying these different layers, you might have more weak points in your propellant. So, and residual stresses, like you mentioned, is also very important to quantify. So this is all work that we want to continue off of this.
Okay. What's the largest article of energetic material you've 3D printed? And do you have any pictures of the current setup you are using?
Yes, so everything has been small scale so far. I think the biggest I've printed is maybe a few inches by a few inches, but there is intent to scale this process up. First, we need to understand the current process better, especially with process monitoring. But yes, we do have plans to scale it up. And I'm trying to think, there might be some presentation images online of some setups, but I'm not entirely sure. I know we've taken pictures. I just don't know if they're out there publicly.
Right. Understandable. What size have you worked up to, and do you believe, oh, you kind of just answered this, and do you believe the process is scalable? So.
Yes, as far as scaling, I think we're going to need something besides pre-mixing propellant and putting it in a syringe. It's going to have to be some kind of continuous process, mixing process, feeding process. So that is something we really need to think about. But yeah, I do think it can be scaled up. I mean, there are people who print, concrete, which is kind of similar in the sense that it's heterogeneous, and they can do that at large scales. So I think, we don't necessarily want to print houses, but I think we can scale it up. We just have to be creative about it.
Right. What differences do you see in the extrusion if vibration isn't included? Will it not extrude or just extrude less? Does the extrudant drip ever, or the movement is just based on if the vibration is enabled?
Yes, so if you don't have vibrations, the technique is basically direct right or direct ink right. So the limitation with those systems is typically you don't want to go above a certain viscosity, because it can be very difficult to extrude that material through a very fine nozzle. So typically the nozzle diameters are larger with direct right. They typically try to use more ink-like formulation rather than slurry-like formulations. And they print slower than vibration-assisted printing, but it's not to say you can't print propellant with direct right. It's just going to be maybe not as fast. There might be some limitations to it, but it's not to say like ours is the only technique for printing propellant. It's just our advantage is that we can print more viscous propellants that don't have to be ink-like.
Right. Oops, I just skipped one. Don't know how to go back.
Oh. Yeah, so...
No, your value went higher than TMD?
Yeah, so this is measured from Archimedes' principle, and obviously there's a bit of error. So I was including the error in that measurement. So, I mean, it's pretty close to 100%. So.
Okay. Have you been able to demonstrate overhangs on 3D prints?
So I have not specifically, but there have been some other students working with this process, and they have demonstrated this with clays. Actually, in our first paper, I think when I was describing the DAP process, there was an image of a pirate ship in there. So I think there were some overhangs in that image. So it depends on the material. I haven't necessarily shown it with propellants yet, but that could possibly be enabled by the photo curing.
Okay. What are the major roadblocks you see for scaling? Is there a rocket motor size you have set as a goal?
Like I was saying before, the feed system is going to be really important. Handling that amount of energetics safely is another concern. I think the mechanical properties of large-scale printed propellant is going to be very interesting because it's going to be very different than cast propellant. So I think we're going to have to really show that we can overcome some of those mechanical challenges in the properties. So that's what I see as the biggest potential roadblock. If we really sacrifice mechanical properties from that, then that could be a problem. But that is for us to find out.
And kind of along with that, one that I have, is there temperature issues that you see as a roadblock?
Do you mean in the printing process?
Yeah.
Yeah, so actually with vibration-assisted printing, we don't see a lot of heating with our propellant mixtures. I think the highest it got to was about 30 degrees Celsius. But you will see a lot more heating if you use something like a clay, for example, because it's a lot more viscous than propellant. So it could potentially be an issue, but I have not seen that as an issue for the propellants I've worked with.
Gotcha. How do you evaluate layer-to-layer cohesion? Just through burn rate experiments?
I haven't specifically looked at layer-to-layer adhesion yet. I mean, there are different, potential peel experiments you could do or tensile testing or whatnot. But I think the point of the burning rate experiments is that at high pressure, when you're burning a propellant, it's almost, how do I describe it? Basically, if there's a defect, it doesn't have to be very large. The flame will enter it. So it's kind of a test of what is the quality of your propellant in a direct way, because the higher the pressure, the easier it is for the flame to go through a smaller gap, essentially. And it will be very, very, very small, like I think, probably micron level size. So it's not really testing layer-to-layer cohesion, but it's just kind of an overall metric of combustion quality, I guess, for lack of better words.
Okay. And we have one that just came through. Is there a use for printing propellant particles, such as powder for conventional guns?
So you mean there's a use for printing the powder in a specific pattern or something?
I guess using it for not necessarily for like rocket motors, but on a smaller scale for like normal weaponry instead of like gunpowder.
I mean, I think this technique is going to be most useful at small scales. I guess I'm a little bit confused by the powder part, but I think it's going to be easier to tailor. I think it's going to be more economical at smaller scales, because if you're trying to, print much larger motors, I think it's going to take potentially longer, or it may not work out as well as if you're making larger systems. So I think the highlight would be small scale and then high tailorability at small scales.
Okay, and I found the one that I accidentally skipped. So do you have any data on bulk mechanical properties of your layered propellants?
Not yet. That is definitely something we are looking at on the next step, especially with the photopolymers. So.
Right. Yep. HTPB contributes as a fuel and contributes to performance. Does your photocure binder have comparable energy density to HTPB?
So with this, in the second study I was talking about, I haven't really done any analysis on the energy density or high pressure combustion test, but I will say with the first study where we tested that epoxy, it really was not that energetic at all. It burned about 2/3 the speed of the HTPB propellant. So yeah, that is definitely something to consider in the design. How much are you willing to sacrifice on your combustion performance so that you can print these complex shapes. So that's something we need to look at more.
Okay, and to respect everyone's time, I think we're going to wrap up. The final thing, did you have your contact information on the slides?
I think I forgot to put that, but I'm willing to give out my contact information.
Right, and so what I was about to say is that, I know one or two people reached out into chat, and we will forward that to you. If anyone else who has been listening in wants to get a hold of Monique, we'll put her contact information out maybe on our website, or you can reach out to DSIAC if you have further questions, and we will make sure to get them to her. Do you have any final words?
Thank you very much for hosting me. I enjoyed the experience, and I hope that you enjoyed my talk. So,
thank you so much, Monique, and thank you all for attending. And we, like I said, have been recording this, and we will be getting this out. If you have any further questions, don't hesitate to reach out to DSIAC or to Monique. And thank you all, and have a great rest of your day. Thank you so much, Monique.
Thank you.